In the last few lectures, we have seen how we can make the running of engines, machines, mechanical systems in general smooth by taking care of various fluctuating effects. Nevertheless, I think we should keep in mind that in practice it is never possible to make a system completely free from any kind of fluctuating or dynamic effects. Dynamic effects, I mean to say that the existence of time varying forces in the system. And if that be so, that means we have been able to reduce the fluctuations, we have been able to make the smoothness quite close to a desirable level, but never perfectly smooth. And whatever residual fluctuating or dynamic forces, moments, etc. will be present will result in oscillatory movements of the various components and members of a system and the engine. And this oscillatory movement, that means the fluctuating motion of a component about its neutral equilibrium position, is commonly termed as vibration. So, I think our last chapter, or rather last topic of discussion on perfecting the design of machines and mechanical systems will be vibrations. Now, you may ask the question that why it is necessary for us to study this fluctuating motion or vibratory motion, because we have more or less taken care of the various dynamic effects and only some residual amount is left. Now, I think, so therefore, let us first establish that why it is so important to study the dynamic characteristics of mechanical systems or vibrations in mechanical systems. Let us consider a particular case, say a simple cantilever beam. It has a length L and cross-sectional area B by H, where H is the thickness and B is the width. And this is subjected to a static force. What will be the effect of this static force applied at the free end of the cantilever? We all know that it is going to deflect, and it will be something like this. Now, in this deflected position, what happens? We all know that this outer, that means the upper layer will be stressed, subjected to a tensile stress, and the lower one will be subjected to a compressive stress. And we also know from our study of solid mechanics that this is the location where the stress magnitude will be maximum, say it is sigma 0. Now, what we do next? We take up a case where the same beam is subjected to a dynamic loading. But before we take up this comparison, let us also find out the situation where you want to design this cantilever beam. Now what happens? Normally from our design procedure we know that the maximum stress developed here is sigma 0, and let it be so that in this particular case it is more than the maximum allowable stress for this material. So from our experience in simple machine design courses we know that the simplest possible way to take care of this will be that rather than having a beam of height h, we may slightly increase the thickness. That means what we can do, we may increase the thickness. With this increase in this thickness, this new stress which will be developed here will be something like sigma prime, and we know that it will be less than sigma 0. So if we add enough thickness to this beam, we can reduce this stress here, bring it below the maximum allowable level, and that will be an acceptable design. That is the static case. Now in the dynamic case, as we have started showing, that it is the same beam, that means it will have the same length, any length of course, thickness h, and say now that the load is fluctuating. Say simplest possible case, say like this. It need not be cosine, it could be sine, it could be not even harmonic, but it is a fluctuating force. Now if we try to take our experience from here and say that the response of the cantilever beam to this fluctuating force will be like this. That means it will have lowermost and uppermost position, because we are subjecting this to this oscillatory force. Actually this will be also oscillatory. So therefore what will happen in this case, that this point will be subjected to alternately a compressed tensile stress when it bends like this, and a compressive stress as it bends like this. So we can now plot with time the stress here will be something like so highest level is say sigma 0, alternately compressive and tensile. Because now this also becomes dynamic, time dependent. Now suppose we find that sigma 0, that is the maximum stress developed, is more than allowable sigma of that material. So obviously this design will not do, and what we may try to increase the thickness little bit, as you did in this case. By an amount delta H. And we expect that the new stress, that means sigma prime, with this increased thickness will be something fluctuating but with a lower value, But it may happen in fact you may find that sigma 0 prime is still greater than sigma 0, which is definitely not according to our intuitive feeling that increasing the thickness, making the whole thing stronger, so the same load will produce lesser stress. But in this case, when the load is dynamic, we can show, and we will solve some problems in future during this course of this program, that you can show that just in such case adding thickness and trying to make it stronger may have reverse effect. That means instead of reducing the maximum stress when you increase the thickness and making it stronger in the static sense, dynamically it increases the stress, increases the deflection, implying that its stiffness or strength has gone down. So the behavior or the pattern of the characteristics of a system when subjected to dynamic loading may be very different from the case or the situation what we find with static loading. And that is why it is very important to study dynamics of such systems or mechanical vibration in a special way. We cannot extend or extrapolate the results obtained by static analysis into the dynamic case. Apart from this, you will find that there are cases and situations where in a machine vibration is deliberately introduced. You have seen that mixing of concrete or some such mineral processing industries, that a vibration is generated to achieve the desired result. And so we should also know that how to produce vibration, how to control it. So there are some applications for useful application of vibration, and thus a comprehensive study of vibration in mechanical systems becomes also necessary to design such systems. Before we take up the study of vibration in a very methodical, systematic manner, it is desirable that we have a bird's eye view of the whole situation. That means how many types of vibrations are there and what are the types of systems which vibrate from, or the classification of systems from the point of view of vibration. We will all look into these things. So therefore, let us consider the case where now, the classification of vibration can be done from various points of view. So the most common and important classification is like this. This is based on how the vibration is originated or the nature of vibration. So this is a very common classification, but it does not show all the various possible variations in the characteristics. We will see to that. First type of vibration is called free vibration. Free vibration means a system has been disturbed from its equilibrium stable position, and then it continues to oscillate for some time. We know you take a pendulum, we displace it from the equilibrium position, leave it, it oscillates. But that oscillation is without any disturbing agent acting on it, and that is why we call it free vibration. Next type of vibration is a forced vibration. In forced vibration, the body or the system is subjected to a dynamic loading, a force which or moment which is fluctuating with time, and as a result the system also vibrates. So cause of vibration is present, let me say dynamic force or dynamic moment is present. So they are called forced vibration. There is another type of vibration which is neither free nor forced. What I mean to say that here this is definitely, this vibration needs an external energy, but it is not required to make the system vibrate by a dynamic force. Even I am talking that vibration of the vocal cord, there is no dynamic or fluctuating force which is acting on the vocal cord, and this type of vibration is present in many cases. That means when you scratch something, it gives a screeching sound. It means what? That it is vibrating, but it is vibrating not because of a vibrating force is acting on it, but due to the system characteristics. So I cannot show it here. May not be possible to show here. So that kind of vibration, like say the bow of say a violin, you pull it one side, but the string vibrates. Sometimes you write on the board with chalk, a piece of chalk, where there are situations where it will give a screeching sound. The talking, or when you are pressing the reed of the harmonium and pressing the bellow, it vibrates. There is a reed which vibrates at its natural frequency. So all these are examples of vibrations due to an external source of energy, but without the need of a dynamic vibrating force. There are another special case of vibration It is somewhat similar to self-excited vibration. Here what happens, one of the parameters, we will discuss the parameters of vibration very soon. One of the parameters is dynamic. There is no vibrating force acting, but say the stiffness of the system is fluctuating with time. Now that is a situation where again the system may vibrate, and these are called parametrically excited vibration. And I think there are some other types of causes, but they are very special, we will not discuss those things here. These are the kinds of vibrations based on the source of energy. So no source of energy, it is free. There is a dynamic force. There is no dynamic force, but there is a source of energy acting on it. Here there is a dynamic variation or time variation of one of the parameters of the system. So these are the commonly found vibrations which is. Next type of classification will be based on nature of dissipation. That means what about the energy, whether it is a energy conservative system or not. So such cases again we can one can be undamped vibration, which means the total mechanical energy in the system remains conserved. There is no method by which it is being either reduced or increased, whatever the case may be, but the total energy remains conserved and there is no dissipation. There is other case which is of course in nature which is more feasible, damped vibration. Now damped vibration means that energy is reducing. So in this case the vibration continues. In this case vibration suppose is reduced, which is what normally we find. Now damped vibration can be again classified into two. One is viscous damping. This is the nature of dissipation. Which is generally based on fluid friction. We will discuss it in details. Or it can be Coulomb damping. Where there is solid friction, that means friction between two solid surfaces rubbing against each other. There also energy is dissipated, and that type of energy dissipation is called Coulomb damping, and other is material damping. It means, or we can see that if we take a piece of beam in space where there is no fluid, no air, and we just vibrate it and leave it in space, we will still see that slowly the vibration will reduce. There are internal mechanisms within the material, just like hysteresis. It is called also hysteretic damping, and the rubbing of grains and other crystal boundaries, they involve certain amount of energy dissipation. Energy dissipation means that the energy, mechanical energy, is converted into the worst form of energy, that is heat. In most cases, sometimes little bit of that is converted to sound also. That means that this mechanical energy is being converted into other forms. So therefore vibration problems can be handled according to the nature of energy dissipation present. Next classification we can have based on the nature of the vibrating system. Nature means complexity mostly. So we will see, first we can have single degree of freedom, we will explain later. Then we can have multi-degree freedom systems. And finally, infinite degree of freedom or these are called elastic bodies. So the system complexity can also vary, that it can have a single degree of freedom system. Now single degree of freedom means that, as we know from our kinematics, that only one independent quantity is needed to describe the configuration of the system. multi-degree freedom system means more than one such independent quantities are required to specify the configuration at any instant, and here we require infinite number of independent quantities, or it is a continuous infinitely variable body, and all we can say it elastic body. Then we can have a classification based on vibration type. We now go directly into the nature of the function, time varying function. So it can be simply harmonic vibration, it means a trigonometric function, sine function or cosine function, you know, harmonically varying quantity. That means any parameter or what is representing the vibration varies harmonically. Next is anharmonic but periodic, or we can say periodic but anharmonic. It is not a harmonic function of time. So in this case, it is simply a sine or cosine function. Here it could be something which is periodic but not harmonic. Next is random. See, here of course there is and of course we are not going to discuss it, but the chaotic vibration is also very important, but we will definitely not have the chance to discuss that chaos and chaotic phenomena here. And finally, we will divide or classify vibration another way. Based on the system parameter characteristics. If the parameters are linear, we call it linear vibration. Here we call it the non-linear vibration. That means again it is based on the system. So these are the various ways these vibration phenomena can be classified or grouped, you know. And because this overall view can help us when we take up this study, we should start from the simplest and gradually go to more complicated cases. I think now let us look into the basic elements and the fundamental properties essential for a system to be of vibrating nature. Everything is not capable of vibration. Say for example, I take this and it is not vibrating. I take a football, I just kick it, it just goes, it does not vibrate. But I take a pendulum, displace it, it oscillates. So therefore, I think there are some essential qualities required for a system to have the capability to oscillate. So the basic elements of a vibrating system What are the basic elements? Now, why a system vibrates? Most important thing what is required for a system to have the capability to vibrate is that it must have generally a stable equilibrium position. That means a position where it stays if not disturbed and it comes back to it if disturbed. That means if I have a body, and this is its equilibrium position. Stable equilibrium position. Now, what happens if I disturb it? Say I push it to one side. I push it to this. Since it is a stable equilibrium position, it will try to come back. So therefore, it is essential for the system to have a capability to come back to the equilibrium position. That means its original position will be restored. So this property is called restoration. That is essential. Suppose if you take a ball, you keep it here, I displace the ball, it remains there. So that will not do. But if it is in an incline or in a curved plane, like a say ball or cylinder, then if I displace it, it tries to come back. There is restoration. That can oscillate. But on a flat plane, if I take a cylinder, it will not oscillate. So this restoration is a property which always brings back the system to its original stable equilibrium position is essential. Next, what happens? When it comes here, it picks up velocity and it comes here. But since it has a non-zero velocity, it has inertia. And so it shoots beyond this original equilibrium position and overshoots it and goes to this. This overshooting is possible. Why? It is because of the inertia of the system. That means it must possess some definite capability to continue in this state of motion, which is a velocity when it comes to this, to continue in that, which means inertia. And without inertia, it will not overshoot. So therefore, but as it overshoots, obviously restoration starts acting on it in the opposite direction. So it will gradually come to a stop and come back to the position. But when it comes here again, it has a velocity and it will overshoot and go to the other side. And this keeps on happening. That means just like a pendulum. Now here pendulum comes back to its original position because there is gravity. This force is acting. If you go to space and make a pendulum, you displace it from one position, it will remain there. It will not oscillate. So the presence of this gravitational pull towards the surface or center of Earth, that provides the restoration, for which it tries to come back to its original equilibrium position. But when it comes here, because of a finite inertia, it possesses some momentum, it overshoots the other side. But then obviously it comes to a stop because it is being acted upon by the restoration and then comes back. And this whole process continues. If you consider a situation where there is no inertia, mass is zero, then restoration is bringing back here, but when it comes here, there is no restoration, no force acting, and since there is no mass, there will be no inertia, it will remain there. So these are the two essential parameters or properties of a system which is required to make the system capable of oscillation and vibration. However, there is another parameter which is not necessary for a system to have vibrating capability, but nevertheless all practical systems will have that property, that is dissipation. By dissipation I mean that the mechanical energy which we put into the system when we displace it from its equilibrium position, now that energy gets gradually dissipated to the surrounding by various methods. So like here, there may be air here and air friction will dissipate energy. There may be solid friction in the hinge here, that may dissipate energy, and so on. So therefore, though this energy dissipation is not essential for a system to be vibrating in nature, but it is present nevertheless all the time. So there will be three parameters which will play the predominant role in any oscillating system, that is inertia, parameters are inertia, restoration, and dissipation. In common language, it looks, this is, we call the mass or moment of inertia if it is angular motion. This we call the spring stiffness in case of elastic, or gravitational pull in case of gravity based system, and this is the damping, which is the common language for describing dissipation. So these are the three fundamental parameters of any vibrating system. Now how do we handle vibrating systems mathematically? Now as you know that whenever you solve a physical system mathematically, the first thing what we do is develop a mathematical model. So one must keep it in mind that whatever may be the subject, whatever may be the branch of engineering or science we are doing, whenever we are writing an equation to describe the behavior or characteristics of a physical system, we are not really doing it for the actual system, which is in general infinitely complex if we go to the molecular level or subatomic level. What we do, we make an approximate mathematical model which more or less behaves in a similar way as the actual system, and we only solve the mathematical model. So here also exactly that is going to happen. When we try to solve the vibration of a mechanical system, we don't solve the actual system, we actually write down the equation of motion for the mathematical model that we will develop. So next thing what we have to understand is modeling of a system. The most important or rather basic idea behind mathematical modeling in case of a vibrating system is lumping of parameters. And the models we develop following this principle, lumping of parameters, are called lumped parameter model. What is lumping of parameters? As the language indicates, that these are the important parameters, we lump them. Now in a system, say for example, take a cantilever beam with a heavy weight at the end. Now this is a vibrating system. If we disturb here, it can oscillate like this. The whole system oscillates. Now here where are these parameters located? Say this system has obviously inertia. Now where is that inertia present? In reality, you can say that every particle of this which is moving has inertia. So therefore inertia is distributed over whole thing. But I think from our common sense, engineering common sense, we know that this particular beam, which has a mass which is of much less compared to the mass of this, and the predominant job of this cantilever spring is to provide restoration to the system. That means if we displace it from its equilibrium position, it comes back to the original equilibrium position, and that is the job which is being done by this. What this block is doing, of course, a block is also not a 100% perfectly rigid body. It also has certain degree of elasticity, but it is so rigid, that means its elasticity is so negligible that its predominant role which is played is just to provide inertia. That means here we find that we can say that this is providing inertia, that is the predominantly the mass. This is providing the restoration or acting as the spring, and the dissipation which is going because of the material damping in the beam which is undergoing distortion and friction with the surrounding air of this and this, all these things are causing dissipation. Now what lumping means, that we can say that okay, this system is rather more or less equivalent to so here we have lumped the parameters. We have lumped the mass as m, lumped the stiffness of this as spring k, and the dissipation by a dashpot. We will come to these things very soon. So therefore, as we see that in general what we will do in a mechanical system, we will extract the basic function or basic property of that. It means who is providing or which part is providing the predominantly the inertia. Like that, this is providing predominantly the restoration, but it has nevertheless inertia also. It also has nevertheless some amount of dissipating capability because of its hysteretic damping, but its main job is to provide restoration. So that's why we call that this is the spring. This also has internal damping, it has certain amount of stiffness, and it has predominantly inertia. Its primary job is to provide inertia to the system, like that. So this is precisely the principle of lumping of parameters, and therefore this is the actual system and this is the lumped parameter system. Now before we take up more such cases, we should just have some little idea about these parameters. Inertia. Inertia means it will be a mass when the movement is linear, or it can be a moment of inertia I when the motion is oscillatory. Restoration similarly can be simply a spring or a torsional spring. This is a linear spring. Here it is like this. Restoration can be gravity based, we have already seen, not necessarily elasticity based. So we can have basin like this in which this is oscillating, or this also is oscillating in a horizontal surface. Similarly, dissipation again can be three types, as you have seen. One is simply the fluid based. What this does, there is a piston with some narrow holes, and that piston moves in a cylinder. And it is completely filled up with a viscous fluid. So when we pull it, what happens? This side the fluid goes through these holes to the other side, and during that process it provides adequate amount of friction, and that is fluid friction, which is proportional to the velocity. The other kind of dissipation of energy could be simply, and this is represented symbolically by this symbol. This is called viscous damping or a dashpot. There can be solid friction, as you know. Here there will be coefficient of friction mu. The solid friction is represented by this symbol, and here the force is F. Here of course the force will be C into velocity, if V is the velocity. Here it does not depend on velocity, it is constant because it is solid friction. So these are the kind of parameters we have. We have dissipation, primarily these two types. Material damping we cannot show, it is hidden inside the material. Restoration can be primarily elasticity based or gravity based in most cases. Inertia can be a linear inertia represented by mass, and rotary inertia represented by a flywheel or a rotary cylinder. Here the stiffness is told A. Here torsional stiffness is given by this. Torsional stiffness sometimes can be a coil spring also. Here also it is angular motion which is resisted by this coil spring. Here it is the gravity, and these are the dissipation. So lumping of parameters, what we have been discussing, is important because only once we have lumped the parameter we can talk about forming an equation of motion, whatever we may say, that is the mathematics or the equations relating to these properties K, M and C and the displacement coordinate. We can derive some relationship between these or among these, which we solve and tell that this is the system's response. Now of course one thing is correct, that sometimes suppose if we have a thin steel spring like this and a mass at the end, we can tell that fine, this is the mathematical model. We can have an example from the angular case also. But suppose if we have to consider the vibration of a beam itself, cantilever beam, like a reed. So you displace it, it vibrates. Then how do you do lumping of parameters? It becomes very difficult, as you can see, because all the properties have been smeared into one body. Inertia is there all over distributed. Restoration is provided by the whole body's elastic properties, and dissipation also is predominantly distributed within it in the form of hysteretic damping, though there may be some damping when it moves relative to the surrounding air. So in such cases it is of course not possible to do lumping like this and get results, though sometimes some very crude approximate models are developed. So therefore we have to identify that which part of the body's predominant property is what. Like say for example there may be two such cases, like say if we have this and maybe another one. Then very obviously this part will be modeled as this without the damping if we neglect it, and this part will be described by another one. So modeling will be like this. Now another important question you have to keep in mind while developing the model, how accurate it should be. Like say some people can model it like that okay, we can divide it into 4 and each one we try to represent by a spring mass system. So there will be in series 4 spring mass system. It will give some result which will be near to this, but obviously not exactly equal to the actual beam. But if you divide into more number of sections, obviously result is going to be more accurate. So therefore, if we want to make the model very accurate, that means representing the original physical system in a very faithful manner, then it is going to be obviously more complex. Solution will be more difficult, but the accuracy of the result also will be definitely much better. So it is always a kind of give and take. It's a balance which one has to strike, that how accurately the result is desired, and based on that we should develop the model. If the result required is not necessarily very accurate, it is pointless to go through the horrendous task of a very accurate model with lots of complexities and spending a lot of computational time in solving the system. So therefore, we should always find out that how the complex or how accurate the model should be. Another important thing what we should discuss at this stage is the degrees of freedom, which I mentioned. It is coming again and again, so I think it is better to discuss here. The idea behind the degrees of freedom is known to you all, I am quite sure, but again we will just quickly revise our memory or refresh our memory. This is related to our modeling, because if we don't require very accurate result, in most cases when we do the parametric modeling, we can try to get a simplest possible single degree freedom system mathematical model. They are the simplest things. So therefore, we see that what these degrees of freedom are. Now, degrees of freedoms are the number of independent quantities required to describe a system's configuration. So, a simple thing which is equivalent to is only one quantity is required, the displacement of the mass from its equilibrium position. So it is single degree freedom system. If this system is something like this, obviously we have to specify the displacement of the two masses, and it will have 2 degrees of freedom. So degree of freedom in this case was 1, in this case it is 2. And say for example, similarly a gravity based system also you can consider. Say pendulum, we have to only give theta, only one quantity to specify its configuration. It is single degree freedom system, but if there are 2 pendulums joined like this, then obviously we have to specify both theta 1 and theta 2 independently, and the number of degrees of freedom for this case is 2. In case of elastic bodies, like say beam, when it deforms, it can deform in any manner, and to represent a deform, you have to express the displacement of infinite number of points describing this beam, and therefore such cases n is going to be infinity, or these are continuous bodies. Sometimes it is not necessary that one has to have more than one lump body to have more than 1 degree freedom. If we take an object is moving in 2-dimensional space, say this plane of this blackboard, and it is constrained to move with the help of 3 springs, then if it is confined to this plane, even a single particle like this will require two quantities to be specified to give the exact description of the configuration. So, it will also have 2 degrees of freedom, though there is only one particle. Similarly, if this particle is resiliently supported so that it can move in 3-dimensional space, even a single particle will have 3 degrees of freedom. Sometimes, if rotational motion of is also there, that means this supported by springs, so here, if you select any point, say center of mass of the body, then it will require 2 degrees of freedom to describe the location of the center of mass, and one more angular position, angular coordinate you have to specify to describe the orientation of this body. So, though this is a single rigid body, in plane motion it will have 3 degrees of freedom. So, therefore, the number of degrees of freedom are necessarily not associated with the number of particles, but in the most general case, one rigid body in 3-dimensional motion can have 6 degrees of freedom. A rigid body in plane motion can have 3 degrees of freedom, and a particle in plane motion will have 2 degrees of freedom if it is confined in a plane. However, in such cases, we confine their motion in one direction, like this is moving along a curve, circular curve. Here it is moving along a straight line. So, in such cases, they are not actually moving in a plane. Therefore, it has a single degree of freedom, as very clear from this picture. So, when we do modeling of a system, another very important point emerges, and we should at least discuss not in details, but briefly at this stage. That means these parameters, what should be the nature of these parameters? So, we are again continuing our discussion on the lumping of parameters and modeling, mathematical modeling. The important thing in this modeling you have to also keep is that so, if we take the case of a simple spring mass system, its equilibrium position is this, and its displacement coordinate, velocity and acceleration, they are x, x dot and x2 dot. Now, when the system moves, there will be 3 forces involved, as you will see. One is the force of inertia. If we plot with minus x2 dot, which is minus mx2 dot, and obviously this is a straight line. We can consider it a straight line for almost all engineering problems, mainly because m remains constant. Unless we take the relativistic effect, which is absolutely unnecessary for most of the problems we solve in mechanical engineering, m is constant, and so the inertia force is a linear function of the motion parameter x2 dot. If we take the damping force or dissipating force, which is minus c x dot. Here again we can see that in reality it will be a straight line up to some time, but then after some time it may vary from the linear property. When x velocity becomes very high, it may not remain, that means the flow may not remain laminar and it may not maintain that linear dependence. So here you will find that we have a range in which it can be considered as linear. But if you go beyond that, then the parameter which represents the energy dissipation by viscous damping cannot be treated as linear. Finally, the restoration is again appears to be linear, but we all know that if we stretch a spring too far, then it tends to become harder and harder and harder. So therefore, the linear relationship between the force and this stretch is only up to a certain point. So therefore, in reality, exactly speaking, none of these are linear functions. But when we develop the mathematical model, we treat the whole system as linear. That means A is constant, C is constant, or this is proportional to x dot, this is proportional to x, this is proportional to x2 dot, like that. They are all linear functions of the respective motion parameters. But in reality, none of them are exactly straight line relationship. But if we don't want to make our problem absolutely difficult, I think we can treat all of this. That means we can consider that we are operating only in the linear range. And that is the case. Normally what will happen if we restrict ourselves to the solution of small vibration. In general, when we solve problems, we have to keep in mind that the small vibration or oscillation which we are analyzing, that is of small magnitude, and that in most cases will rather justify our assuming the system parameters to have linear relationship with the respective motion parameters. We will now have to go to various other kinds of general discussions. One I think we will take up later in the next, before we take up exact problems one by one. It is the type of excitation which we have already mentioned. It can be harmonic, it can be anharmonic but periodic, it can be self-excited, it can be base excitation, it can be force excitation, and of course it can be random. So next session we will start solving problems and take up the problems one by one, starting from the simplest and going to more complex cases.